YouTube channel. In this video, I am going to discuss about force acting on a current carrying conductor placed in a magnetic field. Topic problems, mainly for NEET and JEE students. Okay, first we will do a quick review about force acting on a current carrying conductor placed in a magnetic field. Okay, if a current carrying conductor is placed in a magnetic field, it will experience a force. That force is equal to I into L cross B. Okay. Otherwise, we can write ILB sin theta. This is the force. Clear? What is I? I is the current, L is the length, B is the magnetic field. Okay. So this force is perpendicular to the plane containing L and B. How we can find out the direction of F? F direction can be found out by using Fleming's left hand rule. Fleming's left hand rule or right hand rule. Okay, so first we will see how we can apply a left hand rule. Okay, so I am consider the magnetic field is to be acting like this. Okay, so there is a current carrying conductor. Right. Okay, we will see how we can apply the Fleming's left hand rule. Fleming's left hand rule. Use your left hand. Stretch your three fingers, thumb, forefinger, middle finger in mutually perpendicular way like this. Okay. Place your forefinger in the direction of magnetic field and middle finger in the direction of current. Then thumb will be the force direction. So you place like this. Here the magnetic field is into it. Current direction is like this. The force is upwards. Okay. This. So here forefinger is to be what? Forefinger is magnetic field, then middle finger I, thumb force, thumb. Okay, the same thing we can find out by using right hand rule. In the right hand rule, place your right hand in the direction of first vector. Right hand is based on the cross product. Okay, so any cross product we can apply the right hand. Okay, so I place my right hand in the direction of first vector, that is in the direction of L, and curls toward the direction of second vector, that is B. That means acting into it. Like this I curl, so I got upwards. Okay, like this I place, curl like this, so I got upwards. Okay, so the same direction we got by using Fleming's left hand rule and then right hand rule. Okay, this is about the theory. If you want to know more about this theory, please refer my other video. Okay, clear? Okay, now we will see the problems. What are the type of problems are to be asking in NEET and JEE based on this topic. Okay, so first we will do the type 1. In the type 1, they are to be giving a diagram. The magnetic field they will give and the current carrying conductor they will say they have to find out the force direction. Okay, they will ask like that. You can expect like this. Okay, so like this. If the current is to be like this, magnetic field is to be like this, how we will find out the force direction? Okay, so how we can find out? By using Fleming's left hand rule or to be right hand rule. Okay, so Fleming's left hand rule I am going to apply here. Here the magnetic field is going into it and the direction of the current is to be like this. So what I'll get? I'll get downwards. Okay, this is the force direction for this case. Okay, then second, if the magnetic field is like this, the current is to be acting like this. What about the force? What about this? The magnetic field is coming out. Okay, the direction can be found out by using Fleming's left hand rule. Okay, so I place my forefinger in the direction of the direction of magnetic field and this middle finger is the direction of current. So if the direction is upwards, this is the force direction. Okay. Then next to third case, if the magnetic field is like this, what about the force acting on it? Here. So here, magnetic field and current are in the same direction. So the net force is to be here is to be 0. Is 0. Okay? Because theta equal to 0. Clear? Okay? Then next case. Third one. If the magnetic field is to be like this, current is to be like this. What is the force direction? You have to use by using Fleming's left hand rule. Place your forefinger in the direction of magnetic field and current in the direction. Okay, current direction in the middle finger. So like this you have to place, you get into it, going into it. So force is to be like this, you will get. Okay, then these are the type of the based on force direction. Clear? This is in the type 1. Now we will see type 2. What is type 2? There is a circular current carrying conductor of radius r is placed in a perpendicular magnetic field, and what is the tension acting on this wire? We need to find it. Okay, so this is a important type of question. You can see in the previous year advanced level question. Okay, so we all know that a current carrying conductor placed in a magnetic field, it will experience a force. Okay, so here this is a current carrying conductor, it will experience a force. That force can be found out by using Fleming's left hand rule or to be right hand rule. I am applying here right hand rule. So I place my right hand in the direction of current, curl towards the direction of magnetic field. So I get the force direction is this direction. This is the magnetic force. Okay, due to this magnetic force, what will be happen? There is a tension is acting on this wire in this direction, this direction. Okay, so I am going to find out what is this tension. Okay, for this they are given us the radius is to be r. So I am consider this is the center. I am drawing a radius. This is the r and this is also r. This is the center. Okay, this angle I am taking as d theta. Okay, so this tension I am going to split into two components. One is to be this and one is to be like this component. If this is d theta, that means if I will be consider this radius, I am going to consider like this. Okay, now you can see that. If this is to be the d theta, what about this angle? This angle is to be d theta. Okay, and for this line, this is the perpendicular, and for this line, this is the perpendicular. So we can say that this is also d theta. Okay, if this is d theta, what about this? This is t cos d theta, and what about this? This is t sin d theta. Okay, clear? The similar way here also tension I am going to split into two components. Okay, one is to be along this direction and another is to be in the downward direction. Okay, so this will be theta. Okay, d theta. Okay, so this is t cos d theta, you will get. This is t sin d theta, you will get the similar way. Okay, so here t cos theta and t cos d theta and t cos d theta will be cancelled. Only this component only remain. That is t sin d theta component only remaining. Okay, so this component is produced due to magnetic force. So we can equate. What is the magnetic force direction? That is, we already got it is acting in this direction. That is the magnetic force direction. Okay, so we will write like this. What is the magnetic force? This I am naming it ABC. Okay, so magnetic force is equal to what? I can write it 2 sine d theta. Okay, this is the magnetic force acting on this portion AB. What is the magnetic force acting on AB? That is FB on AB is equal to I into AB. It is to be considered as a straight line. AB, B, and sine, here the angle is to be perpendicular, here sine 90. So what you will get? IAB. B you will get. Okay. Next we have to see what is B, AB. So for this triangle, what is d theta? D theta equal to AB divided by R. So this is to be considered as a structure. Okay. So for this AB divided by R we will get. So what about AB? AB is equal to d theta into R you will get. Okay. So this is to be a capital R. I am going to write here. Okay. This will substitute here. So what about FB? FB is equal to I into d theta R B. Okay. This is the force acting on AB. There is another portion also there. That is BC. Okay. So the net FB, what you will get? The net FB is 2 times of this. Okay. So we can write it as 2I d theta RB is equal to how much? This is also 2 times here. What needs to be? T sin theta d theta here and this side. Okay, so 2 into T sin theta sin d theta. Okay, for a smaller angle, if theta d theta is small, if d theta is small, what about sin d theta? Sin d theta is nearly equal to d theta. So we can write here. This 2 and 2 we can cancel. So I d theta BR is equal to T d theta. D theta we can cancel. So T is equal to what is it? IBR. I is the current, B is the magnetic field, and R is the radius. Okay, this is the tension acting on this wire. Clear? Okay, this way we can solve this type of problem. Okay, this is an important type of problem. Okay, then next you will see the third type. Okay, what is the third type? Find the net force acting on the square. Find the net force acting on the square. So listen here. This is a square. In this square that is placed in a magnetic field. What is the net force acting? I am going to name it ABCD. Okay. So this all sides are to be equal. So I am going to find out what is the force acting on AB. The force acting on AB is equal to what? It is to be 0 because what? Theta is equal to 0, sin 0, because the force acting on a current carrying conductor is equal to what you will get? ILB sin theta. Sin theta is here 0. Okay. Then next, what about the force acting on DC? DC also 0. That is because theta is equal to 190. Because sin 190 is equal to 0. Okay. Next, we will find out the force acting on AD. What is the force acting on AD? That is I. We will take it as the current is to be I. Okay. I into what is the length? That is AD into the magnetic field is B. Sin 90. Okay. So what I will get? IAD B we will get. What about the direction? The direction can be found out by using Fleming's left hand rule. Okay. So I will place my forefinger in the direction of magnetic field and the middle finger in the direction of current. So I will get the force direction is into the plane. So this is the force acting in is into it. Okay. Clear? So that is FAD. Okay. Then This is the one force is acting here, that is FAD. Okay. Then next I am going to find out the force acting on BC. Force acting on BC is how much? That is I into BC B sine 90. Okay, so sine 90 value is to be 1. So I BC B we will get. Okay. What about BC and AD? BC and AD are same in magnitude. So FB is equal to IBC B. Okay. What about the direction? The direction is to be found out by using Fleming's left hand rule. You place your forefinger in the direction of man field and the middle finger in the direction of current and thumb will release. That means it is to be the direction is upward. So FBC is in this direction. So FBC is acting upward. So you can see that FAD here. FAD is equal to FBC. These are equal in magnitude and opposite direction. So what about the net force is equal to what? That is force acting on AB plus BC plus BC plus and AD. This total is to be 0 we will get. Clear? Okay. This is the type 3 problem. Okay. Now we will see type 4. Current carrying conductor balanced in a uniform horizontal magnetic field. Find the mass of the conductor. Okay, this is a current carrying conductor of length how much? 10 centimeter. L is equal to 10 centimeter, that is 10 into 10 power minus 2 meter. Carries a current, that is 2 ampere. It is balanced in a magnetic field. That means due to this horizontal magnetic field, this conductor is balanced here. Then if it is balanced like that, what is the mass? Okay. So what is the B value? 0.2 Tesla. Okay. What are the forces are acting on this conductor? This conductor is placed in a magnetic field, so it will experience a force. That force F is equal to magnetic force F is equal to, that is ILB sin theta. Here current is in this direction, magnetic field is like this, so theta equal to 90 degrees. So what about you will get ILB, you will get sin 90 equal to 1. Okay. Then what is another force? So this is the force due to the magnetic force. Okay. How we can get this direction? This direction can be found out by using Fleming's right hand rule. Okay. I place my right hand in the direction of current and curls towards the direction of magnetic field. So a curl like this. So I got the upward direction. That is the magnetic force direction. Okay. What is other force acting on it? Other force acting on it is gravitational force. That is acting in the EMG. Is acting downwards. Okay. So if it is balanced, the downward gravitational force is equal to the upwards magnetic force. Okay. So FB is equal to mg, that is ILB is equal to mg. What we need to find out? Mass. This m is the mass of the conductor. So m is equal to ILB divided by g. Okay. What is the I value? I value is 2 ampere. And what is the B value? B value is 0.2 Tesla and the L value is 10 into 10 power minus 2 divided by G value. We can take it as 10. This 10 and 10 is cancelled. 0.2 into 2. How much you will get? That is, you will get it as m is equal to 0.4 into 10 power minus 2 you can get. Okay. This I can write it as 4 into 10 power minus 3. Like that I can write. So this is equal to how much? 4 gram, like that. So mass of the conductor is equal to 4 gram. Okay, this is the type 4. Okay, now we will see the type 5. Okay, what is the type 5? There is a circular conductor is placed in a magnetic field, in a perpendicular magnetic field, what is its tendency? Try to expand or contract or move towards positive x or move towards negative x. Okay, we will see it. So in this circular conductor is placed in a perpendicular manifold, so it will experience a force. Which force? Magnetic force. That magnetic force direction can be found out by using Fleming's left hand rule or right hand rule. I am using the right hand rule. I place my right hand in the direction of current and curl towards. This is the magnet. So I will get the force direction is this. If I will find out the magnetic force direction, here is I will get like this, here I will get like this, and here I will get like this. That means it tendency to expand it. Okay, but the net force is to be 0. But its tendency is what? Its tendency is to be expanded. Okay, so this is the answer. Okay, clear? This is about the type of fight. These are all the important type of problems in this topic.
Thank you for watching the video. Please subscribe my channel. If you like this video, please put like